If you would like to be subscribed to the Telecom channel, please go to the Telecom community website, and in the very beginning of the website there is a link to the Telecom channel, so you can use it to get the latest updates. And the first topic is about applications of artificial intelligence in telecom. So, please.
Thank you, Lee, for introduction. Let's start. Thank you for coming today in the morning, and I'm so proud to stay here in front of such a great audience. Today we'll have several talks about the applications of AI in telecom in our company already. Okay. So I decided to talk about the world in general and how the world looks like and how the signal goes from the server to the user. For example, when you're watching the YouTube, you make a request and then you see the movie. But what happens between? And in between, we are in between actually. So on the left side, in the California, you can see the servers. For example, the YouTube, what happens in the web. And then the signal for different users is packed together to go through the earth. And you can see that, for example, in New York, the signal splits. Something goes to South America, something goes to the Europe. And it happens actually inside some very large IP networks. The signals is packed inside some optical fibers and goes with the speed of light. That's why video is very fast. But on one hand, you can see Ivan and Masha, they're requesting something from the web. The Joanna from Brazil also requesting something. And we have to create some optimal scheduling of how to distribute our resources inside very large optical networks. This is the big optimization problems. And this will be included in the talk of Yefim Boyer, which will be in 11 a.m. today. I'll just say briefly. He will talk about very interesting things. And for example, when someone is building a house, for example, this is solar house, they can cut the fiber, optical fiber, which is going down, and then there will be no YouTube, no Facebook, and so on, and maybe in India, because this signal goes through Moscow. Okay, then I have to check it out. Once the signal came to some local city, Moscow, then it switched to the wireless network. That's what all we use in our cell phones. The same scheduling problems are solving at this level, and also today there will be a talk from Irina about some reinforcement learning about how to create the optimal scheduling. Because what we want to do is we want to make people happy. A lot of users is requesting for the resources, but we have one base station, another base station, and for example today there are a lot of users here. And if I say to you, let's watch a YouTube video, then the traffic will be very high. And this is the problem, how to make all of you happy, how to make the speed of video, the quality of video very high. This is some optimization program, and inside there are also some machine learning techniques. But Huawei, first of all, is a hardware company. We create a lot of devices, and the design of these devices, some new things in these devices, this is our key point. This is our competitive advantage. That's why our company became so large, so big, and that's why you know now about the smartphones and so on. So first of all, we started from the hardware, and hardware is still our biggest business, I think. And for example, in the base stations all around the world, the Huawei equipment is installed and is doing his work. And this is the very challenging task. I will talk in my presentation at 4 p.m. About how to build the AI model, which can be included in the very small chip, in ASIC. This is some special crystal that conducts the computations. And I will most of all focus on the sparsification of the networks, how to reduce the complexity of the AI models. Then you can ask, how much can I reduce the complexity? I can ask a question, whether some of you would try to reduce the resources, the computational resources of your AI models. Just show me with your hands. Wow, I see some hands. Yeah, this is the key point here, because we are fighting for the power consumption in these devices. They doesn't have to heat so much. And this is the challenging problem. But first of all, when I saw the requirements that we have to reduce from millions of parameters to 1,000 without any loss in the performance, it was very surprising for me. But we have found the ways. I will talk briefly about that in the presentation. Also, beside that, you can see a lot of other applications in the different parts of the stack of technologies. For example, there in the bottom, there is a forward error connection that I call. It is also called the channel coding. The problem is that when the signal goes from antenna to the user, it can go directly. This is the best case. This I tried to show in the picture. The best case when it is in the line of sight. Then the quality is perfect. But you can have a lot of reflections. You can have some distortion, and that's why the coding is applied to finally to distribute the signal to the user. But what is the parameters of the coding? Which are the optimal parameters of the coding? We can adjust them, for example, using some reinforcement learning techniques or ordinary machine learning techniques. So even in this field, which did not rely on the AI anyhow, now there are a lot of solutions based on the TensorFlow when they try to build this coded system inside the TensorFlow and optimize some parameters to make finally the people much more happy. Okay, so you can see the weights. I tried to show that the world is standing on 3 weights. Of course, you know that it is a joke. The world is actually standing on much more other different animals, the elephants, the turtles, and so on. But I'm talking only about some three departments of Huawei. So the optical networks, transition and access, the Wi-Fi and wireless networks, which are similar in some cases because it is wireless networks. And finally, about the global technical service. What does it mean? So you know, you all served by some cellular operator, the carrier, MTS, Megaphone, and whatever. And we are supporting them because the surprising thing that in some cases we know about the networks much more than some particular carrier. That's why we can help them, and that's why they give their responsibilities to us. And so we help to maintain the whole network, and we develop the global solutions about the networks that help the network not only in Moscow, not only in St. Petersburg in China, but all over the world. Also for Japan too, in Brazil. Okay, so I talked about some brief introduction about some talks that will be today. And also I have to mention that there will be a talk about neural architecture search, also from Huawei, not related to Telecom, but also from our computer vision department. And it will be also interesting. It will be in the same time with my talk on 4 p.m. So you have a lot of abilities to choose what to listen. I think it's great. Okay, and so I'm going to talk small about one problem related to the last department, the global technical support. It will be just an example how we switch from the physical modeling, from some engineering techniques which were popular previously, and to the machine learning. And finally, we understand that we cannot rely only on machine learning, we cannot rely only on physics. We have to mix this all together, we have to find the best architectures of the model and get the best performance. This is one typical situation. We want to know the coverage of the wireless network in the city. So this funny picture is a city, and this ball inside is some base station, which is trying to distribute the signal around in the area. And what we want to do, we want to understand where the signal is great and where the signal is poor. If we understand that the signal is poor, we can say, okay, we have to optimize the network, we have to rotate the antenna, or we have to build a new station. That's the point for the network planning that I printed inside below. Okay, previously the solution was based on the ray tracing. Some physical modeling when we look at the distributions of rays in the area and try to compute the final distribution within the city. This technology, of course, it has some advantage compared to the other techniques because it is based on the physical laws. And but on the other hand, we have a lot of impreciseness inside our data. We don't know the city in details. We don't know from which materials the buildings are constructed, and so on and so on and so on. And the last thing, and the most important thing, that this physical approach is not reliant on the data that we can measure. That's why the machine learning comes here. Okay, so you can see the cats and dogs. I will talk about that. Everyone loves cats and dogs. What we wanted to do is try to rely on the data that we have. Which data we have? Every time the user is on the street, he reports to the network his signal and his position. If he is if his GPS is turned on. Using this data, the mobile operator can optimize its network. And that's the data that we have. It is on the left side of the slide. The color denotes the value of the signal. And you can see that in some parts, we don't receive anything. Why? Maybe because there is no signal there, and users are not happy there. They want to watch the video. There's no video. But maybe there were no users there. So we cannot say with some insurance about this part of the data. So we have this data on the left side, but on the right side, on the left side, we have some environment. And our hypothesis is that the signal distributes the same way in the same environment. What is the environment? The antenna is in the center of the picture, and the environment is the buildings which are around the antenna, the terrain height, the height of the buildings. There's some other cluster. For example, you have trees, and when you are in the forest, the signal distribution not so great, and so on and so on. So we pose the problem of signal distribution as an image processing problem. And we have this spatial input and the spatial output. Yeah, of course, the spatial output is sparse, and we have to imagine how to pose the problem correctly. But anyway, we looked at the problems from the state-of-the-art machine learning techniques that works with the cats and dogs. There on the right side, they want to predict in which point of the image you see the dog, in which point you see the cat, and where is the background. This is the spatial output. And we use these technologies. Of course, we adapted them and to our case, but that's how we incorporate the machine learning to the place where there were no even machine learning before. There were no benchmarks to compare with. There were no some baseline networks. Nothing. And it was really challenging because from what to start? In image processing, there is a big community who gives us some answers to start from this architecture. ResNet with a lot of layers, try to optimize something there. But here we didn't have any benchmarks. That's why I think it is much more challenging probably than some image processing. Maybe you can hate me when I say this, but we have to be aware in what is happening inside the image processing, inside the text processing, audio processing, to understand what techniques are the best in these fields. This is on one hand. On the other hand, we have to understand how the radio engineering works, how wireless technologies works. And we have to mix this all together to create the new architectures without any baselines. This is really challenging, and it cannot be solved by 1 month, maybe half a year, maybe to get some even additional 1 dBc of the accuracy, we have to spend another 1 year. But this work is really interesting because we are starting from the Telecom. Nothing is clear. Okay, so I said that I said that we can forget about physical modeling, we can just collect a lot of data and to build something that works great. Maybe sometimes, maybe someday, one day, this technology will work like this. But this is not true, and we still need physics, and we still need to incorporate physics in our models. This is the example, so I call it transfer learning here. This points around the building is some measurement reports that we are collecting from the users. Because we know their positions from the GPS, we know their signal strength in the mobile network. But what do we want? We want to understand the coverage inside the building. And we don't have the exact positions from the user inside the building. Why? Because the GPS is not receiving inside the building. The walls, the roof, and so on, and the signal from the satellites doesn't come, and we don't know where the user is. So probably the operator wants to optimize the coverage inside the building, but he even don't know where the problems are, and that's the case. For example, even in our office in Huawei, we had the problems with the megaphone. So we had to call him and say, we have problems. Maybe we talking with some manager who is not responsible with it. So it is very hard to fix. But the guys who are optimizing the network, they see that there are some users with the bad signal, but where these users are, where they are, the GPS is not receiving. So they know that the problems, and how to solve the problems, where the problems are. And that's what this slide is about. So we can collect precise data around the building, and we can know the coverage around the building. But finally, we want to understand the coverage inside. But we cannot use this data that were collected around the building as they are, because it is different data. When signal propagates through the walls, inside the building, reflects from the other walls, it is different. It differs from the signal from the outdoors. And that's what we need to do. We need to collect data around and then transfer them inside to remove the features related to the outdoors, incorporate the features that are specific to the indoors, and work with this data. We can interpolate the coverage inside, but we have to do it in some clever way. I think it is related to the optimal transfer and some other things that you've heard on the school. Maybe we can use some face app or something like that removes some features, that adds some features. Maybe this is our new technology. Just came to my mind right now. But, okay, so we receive the signal on the ground, and we are asking what is inside. But what is on the highest floor? The interesting thing that on the highest floor we can receive some base stations which cannot be received on the ground. Because these base stations, they are standing on some very high buildings. And these signals can be received also on the high floors. But we never see this data from the ground. And that's why we have to use some physical modeling here. We have to mix this approach related on the data and related on the physics together to get the final best solution. And that's what we do every day. Okay, there was some brief introduction about our tomorrow, today talks, about one problem that we are solving to make people much more happier. And now I talk just a couple of words about our department. Maybe this is the fourth whale on which Huawei is standing. We are not so big, actually, we are like a turtle, but we have more than 50 employees. Maybe a couple of years ago we had 30, now 50, and now we have really great plans to grow twice to the next year. We have wireless department, transition access related to the optical networks, which is new. Cloud department, because Huawei is given the cloud services. And for example, the very interesting thing that the optimal scheduling is also interested for them. So they came to us, they say, we have a lot of computational resources like servers, we have a lot of tasks, we want to distribute them. And I said to you that on the other hand, in wireless networks, we have a lot of users which are asking for the traffic, a lot of antennas. We want to build the optimal scheduling there. I was really surprised when I came to Huawei that everyone is needed in this thing. I think even McDonald's wants to have this technology, and I think they have. Because a lot of people staying in the queue, and what McDonald's wants to do to make them happy. Future IP networks. I even don't know what is it. Maybe I thought it is 6G, but I don't know exactly. Something very new. And the guys came to us. They said that we want to hire 10 employees. Let's find them to solve some challenging tasks. Global technical service that I mentioned before, the marketing. Also, we are working for the marketing. Maybe it is for myself. Okay, and a lot of. You can ask me. You can go to our booth. Thank you for your attention, and you can ask me questions. I don't think that we have time. You can ask me when you meet me here. Thank you.